Have you ever stopped to think about what connects the music streaming to your phone and, say, a medical x-ray? They seem like they're worlds apart, right? Well, they're actually both part of this incredible, invisible world of energy that is literally all around us, all the time. Today, we're going to pull back the curtain on this invisible rainbow, the electromagnetic spectrum.
So, let's start with that question. What on earth could your Wi-Fi signal possibly have in common with a hospital x-ray? It sounds like a trick question, but it's not. The truth is, they're basically two sides of the very same coin. They are both just forms of electromagnetic radiation, they just operate at totally different energy levels.
To really get our heads around how that's possible, we have to look beyond what our eyes can actually see. You see, the world is swimming in light that's completely invisible to us. There's this whole hidden spectrum that's been right there, in plain sight this whole time. Think about the colors of the rainbow, right? Red, orange, yellow, all the way to violet. That familiar sight is just a tiny, tiny fraction of the full picture. Our eyes evolved to pick up on this specific slice of light, probably because it's just so common out there in the universe. But believe me, there is so much more going on that we just can't see. Okay, so let's actually explore this hidden world. We're going to map out the whole thing. We'll start with the really long, low-energy radio waves, and we're going to travel all the way up to scale to the super high-energy, really powerful gamma rays.
So here it is, the whole family of electromagnetic waves, all lined up. Over on the left, you've got the long, lazy radio waves. Some of these can be as long as a building. Then you've got microwaves, which, heat up your lunch. Next is the infrared that your TV remote uses. Then there's that tiny little sliver of visible light that we can see. And after that, things get a whole lot more intense with ultraviolet, X-rays, and the incredibly powerful gamma rays all the way on the right.
Now, the key to understanding this whole spectrum is actually a really simple rule. Wavelength and frequency are total opposites. It's like a seesaw. When the wavelength is long and stretched out, the frequency is low. Not many waves passing by per second. But when that wavelength gets super short and bunched up, the frequency goes through the roof.
To really nail this down, we need to pop the hood and look at the basic building blocks of these waves. I mean, what really makes a radio wave different from a gamma ray? It all comes down to just a couple of key properties.
First up, we have wavelength. And it's pretty much what it sounds like. It's just the physical distance from the peak of one wave to the peak of the very next one. For a radio wave, that distance could be meters long. But for something like a gamma ray, we're talking about a distance that is smaller than a single atom.
It's wild. And then you've got frequency. Picture this. You're standing on a beach, and the waves are rolling in. Frequency is simply how many of those waves passed you in 1 second. It's the rhythm, the beat of the wave. Now here is where it all clicks together. Out in the vacuum of space, every single one of these waves, from the longest radio wave to the shortest gamma ray, travels at the exact same mind-boggling speed, the speed of light. And what that means is, if you make the wavelength shorter, the frequency has to speed up to keep pace. They are locked together in this perfect cosmic dance. Okay, so now we get to the really cool part, the hidden power packed inside these waves. And the key that unlocks that power, the secret ingredient, is its frequency. It's the frequency that dictates how much of a punch a wave carries and how it's going to interact with the world around us. And the rule here is incredibly simple. Higher frequency equals higher energy. That's it. Low-frequency waves, like the ones from your radio, are like gentle whispers of energy. But the high-frequency waves, like X-rays and gamma rays, those are cosmic powerhouses. This energy difference creates what you could call a critical line in the sand, the ionizing divide. On one side, you have non-ionizing radiation. These waves just don't have enough oomph to mess with our atoms. But on the other side, you have ionizing radiation. The super high frequencies of UV, X-rays, and gamma rays give them enough power to literally knock electrons right out of our atoms, and that can cause some serious biological damage. All right, so just when you think you've got a good handle on all this, we're about to take a little dive into the completely bizarre and wonderful world of quantum mechanics. Because it turns out light has a secret identity, and it changes everything we thought we knew.
This is the huge question that stumped some of the smartest people on the planet for years. What is light, fundamentally? Is it this smooth, continuous flowing wave? Or is it more like a stream of tiny little bullets, these little packets of something? What is its true nature? Well, the answer came from this really clever experiment. Scientists took a sheet of metal and they blasted it with a super bright, super intense beam of visible light. The thinking was, a brighter light is a more powerful wave, so it should have enough energy to knock some electrons loose. But
Nothing. Nothing happened. It didn't matter how bright they made the light. So then, they tried something else. They used a very, very faint beam of high-frequency X-rays. And bam! Instantly, electrons were sent flying off the metal. This was proof that energy isn't delivered in a smooth wave, but in individual, discrete packets. And this led to a completely mind-bending conclusion. Light is somehow both a wave and a particle at the exact same time. It travels like a wave, spreading out through space, but it arrives and interacts like a particle, delivering its energy in one single lump. We call these little packets of light energy photons.
And this brings us right back around to the key lesson from that experiment. A photon's energy, its punch, comes from its frequency, not from how bright the light is. You could send 1 billion low-energy red photons, and they won't do the job. But just one high-energy, high-frequency X-ray photon has all the power it needs to make an impact.
So, we've learned that light and all electromagnetic energy isn't this smooth, continuous stream. It's quantized. It comes in these tiny individual packets. This discovery completely revolutionized physics, and it really makes you wonder, doesn't it? What else in our universe isn't as smooth and continuous as it seems? What other fundamental building blocks are just waiting for us to discover? Thanks for joining me on this tour of the invisible rainbow.